In this lesson, we're looking at vector functions representing position relative to time. So essentially, we're looking at applying vector functions to act as functions that track position over time. Okay, so really what this breaks down to is that the x component of this function r is xi plus yj with respect to time is a horizontal position, yt is vertical position, and t is a time parameter, so it could be seconds, minutes, just depending on the scenario. The good thing is if we can track position relative to time, then we can also start to consider direction of motion. So just quickly before we go into how this functionally works and how we can determine the direction of motion, we'll just define the position functions for vectors in 2 dimensions and 3 dimensions. So in 2D, position relative to time, which essentially is motion, is defined as t is equal to the x displacement and the y displacement. In 3D, we are looking at the position being defined by an x and a y and a z displacement in the ij and z directions. Okay, to consider motion, let's look at the function r is equal to sine t in the I direction and cos t in the j direction. So we'll try to describe the motion of this particular function. So we'll construct a table. So in this table, we'll consider t relative to x, which is sine t, and y, which is cos t. Now, working in radians and knowing sine and cos are cyclic and start to repeat after 2 pi, we'll do fractions of 2 pi. So let's start with the initial position, which is 0. We'll then go pi on 2, pi, 3 pi on 2, and then 2 pi. And so that will represent one full cycle. Okay, when t is 0, sine of 0 is 0, cos of 0 is 1, sine of pi on 2 is 1, and cos of pi on 2 is 0. T is equal to pi, sine pi is 0, and cos pi is -1. When t is equal to 3 pi on 2, sine 3 pi on 2 is -1, and cos 3 pi on 2 is 0. And then finally, sine of 2 pi is the same as sine of 0, and it's 0. And cos of 2 pi is the same as cos of 0, and that's 1. Okay, so when we consider those positions at specific times, when t is equal to 0, we get the coordinate 0, 1. So 0, 1, when t is equal to 0. When t is equal to pi on 2, we get the coordinate 1, 0. That's when t is equal to pi on 2. When t is equal to pi, we've got the coordinate 0, -1. So t is equal to pi. T is equal to 3 pi on 2. We have -1 and 0. T is equal to 3 pi on 2. And then finally, we get the same position when t equals 2 pi. Now, if we look at that position as time changes, we've got a direction of motion as well. So it seems that we have circular motion, and in terms of direction, it's going to be clockwise. So we have clockwise circular motion. We could have created a Cartesian equation for this as well, so we could have said that x squared is sine squared, y squared is cos squared, and x squared plus y squared is sine squared plus cos squared, which is 1. And we get the same thing. We get a unit circle centered at 0, 0. The only issue is that determining direction of motion is not possible when we're in a Cartesian form like that. Okay, so really that's our focus today. We're looking at any type of function relative to time, and now we'll look at a couple of examples. Okay, so we're looking to describe the motion of the position vector function RT is equal to sine t I cos t j and 2k. So the first thing that jumps out to me when I look at this problem is that the vertical component is constant, so that's not going to change. We're going to get change in the I and j directions, but k is going to remain constant. So if we set up a table, it doesn't have to be a full table. We can just say time, position, and that will suffice. So we're going to do the same thing, 0, pi on 2 pi, 3 pi on 2, and 2 pi. And we'll look at how this changes over time. So if we take the position as a coordinate, sine 0 is 0, cos 0 is 1, and the k value is constant and is 2. When t is equal to pi on 2, sine pi on 2 is 1, cos pi on 2 is 0, and the 2 is constant. When it's pi, sine pi is 0, cos pi is -1, and the 2 is constant. 3 pi on 2, sine 3 pi on 2 is -1, cos 3 pi on 2 is 0, and the 2 is constant. And then finally back to the original position, 0, 1, 2. So to be able to describe this motion, it would help to be able to sketch it. So if we sketch the horizontal or the I and j directions, and then k, essentially what we're doing is we're looking to track up these values, which will be zeros and ones in I and j, up to a height of 2. So the original point 0, 1, 2, so 0, 1, and then 2 is right here. So 0, 1, 2. And we look at 1, 0, 2. So 1, 0, 2 is here. 0, -1. So 0, -1 and 2. And then -1, 0, 2. Now this motion then, in that horizontal plane, raised vertically too. So it's clockwise circular rotation, which is parallel to the horizontal axis, and raised vertically 2 units. All right, so describing the position of that function over time, or the motion of that function over time, we can see that it's very similar to the last example, except it's raised 2 up. Okay, so the last example. Now, this example says the motion of 2 particles is given by A and B. Determine when and where the particles collide. So it's important to understand what we're doing. We've got two particles in motion in 2 dimensions, and we're trying to find the time and the position that they collide. The easiest way to deal with this is equate the directional components. So if we equate the displacement in I, and at the same time we equate the displacement in j, we should be able to get an idea of when these things are equivalent. So essentially we're saying that if they were to collide, then that position 2t take 3 for A, and t plus 2 I in B must be equivalent. Now at the same time, there's t squared plus 10 in the j direction, must be equivalent to 7t in the j direction for A and B respectively. So we get t squared plus 10 must be equal to 7t. Now the solutions of each of these, there should be a common time, and if there's a common time, there'll be a collision at that time. So this one's nice and easy. We have 2t is equal to t plus 5, and when we subtract t, we get t is equal to 5. So for there to be a solution, there must also be a solution when we equate j of t equals 5. So let's have a look. T squared take 7t plus 10 is equal to 0. That will be t take 5 and t take 2 when we factorize it, and thus we end up with a solution t equals 5 or t equals 2. Obviously, the collision occurs when t is equal to 5. We've got that common time. And to determine the position, we can sub this back into both of the equations. It will also serve as a check. So A5 will be equal to 2 times 5 take 3 in the I direction, and 5 squared plus 10 in the j direction, which gives us 7 in the I, and 35 in the j. Now B at time 5 will be 5 plus 2 in the I direction, and 7 times 5 in the j direction, which gives us 7i and 35j. So you can see that those positions are the same, and that's the position of collision. So the particles will collide after 5 seconds at the position 7:35. Okay, that concludes the lesson looking at vector functions representing position relative to time.